Hello everyone, welcome back to Wrath of Math. I'm your host, Sean Ian. In today's video, we'll be going over how to graph linear inequalities, which are just linear functions that relate one variable to a function using an inequality rather than the traditional just equals sign. So we'll go over two examples, and it's pretty simple, it's pretty straightforward. I think you'll get the hang of it pretty quickly. I'm going to assume that you already know how to graph a linear function. So if we have something like y equals 2x plus 3, I'm assuming you know and you are very comfortable with graphing this. If that's not true, then I probably have a lesson or two on that on the channel. If not, surely somebody else does. With that out of the way, let's get into it and look at our first example, which is y is less than or equal to 2x minus 1. So how are we going to go about graphing this linear inequality? Well, first things first, let me set up a plane for us to work on. Alright, so here's our xy plane. We're going up by units of 1 on each axis. So first things first, all you have to do is pretend that your inequality has an equals sign instead of whatever inequality you have, and graph that line. Also, of course, you want to make sure that you have your y isolated and that you're looking at the function in what is effectively slope-intercept form. So we're just going to graph the line y equals 2x minus 1. Now when you're graphing this, it needs to either be dotted or solid. It's either a dotted line or a solid line. If we have a strict inequality, either less than or greater than, we would use a dotted line. But because we have less than or equals to, we're going to use a solid line. So let's graph it. Of course, we know that our y-intercept is -1. Let me use a different color so it stands out a little more. Y-intercept's -1, so we'll put -1 right there. And then we have a slope of 2, so we just go up 2 over 1, up 2 over 1, and we have our line here pretty well established. And I will do my best to draw it. And there's our line, which is sort of the boundary of the region that this function will output, given, an infinite number of x values. So here's our solid line, that's our boundary. Y is less than or equal to 2x minus 1. So this means that y, our output, is less than or equal to all of the values on this line. Since it can be equal to all the values on this line, that is why it is solid. Since it can also be less than all the values on the line, all we have to do now is shade below it. And that's really all there is to it. We shade below the line, and now this covers the shading, we can pretend, goes on infinitely with the line, and this is all of the values that the function can output. It can be less than 2x minus 1, which is why we shade below the line 2x minus 1, and it can also be equal to 2x minus 1, which is why we have a solid line there. So I hope that is clear. Let's move into our second example. So now we'll look at a slightly more complicated one. Let's say we have 2y minus x is greater than 6. So of course, first things first, we need to solve for y. Let's add x to both sides and get 2y is greater than x plus 6. And then of course, divide both sides by 2. Y is greater than 1/2 x plus 6 divided by 2 is 3. Remember, if 2 was negative, we would have to flip our inequality sign to be y is less than this function. But since it's a positive 2, we don't have to worry about that. So here's our inequality that we are going to graph. Let's again get a plane set up so we can see it in action. Alright, so here's our xy plane, and again, we have a scale of 1 going up on each axis. So again, first things first, we just pretend this is y equals, and we graph that line. We graph the boundary of the region, which is 1/2 x plus 3. But this time, y is strictly greater than 1/2 x plus 3. It can't be equal to it. So in this example, we need to use a dotted line. Remember, in the previous example, it was less than or equals to, which is why we used a solid line. Now we don't get the equals to, so we'll use a dotted line. First things first, we'll plot our y-intercept, and again, I'll use the different color. So plus 3, we have a y-intercept of 3 right up here, and we have a slope of 1/2. So that's up 1 over 2, up 1 over 2, up 1 over 2. I could really use some graph paper for this. And here's our line, pretty clear. Oh crap, I forgot to make it dotted. Alright, so that is a really long dot. just assume the whole line is dotted as it should be. So we pretend this is a fully dotted line. Try to ignore this solid bit I accidentally drew in there. So y is greater than this region, or this line rather. It's strictly greater, which is why it's dotted, because it doesn't include the line, and we know that y is greater than this, so we shade above. In the previous example, y was less than the function, so we shaded below. And again, the shading goes on infinitely with the boundary line there. And that's really all there is to it. You get it in what is effectively y-intercept form with an inequality. You graph the boundary. If you have an equals underneath your greater than or your less than, then you'll graph a solid line. If you have a strict inequality, less than or greater than, then you will use the dotted line on the boundary. If y is less than, you'll shade below. If y is greater than, you'll shade above. And that's really all there is to it. So I hope this video helped you understand how to graph linear inequalities. Let me know in the comments if you have any questions, if you need anything clarified, or if you have any other video requests. Thank you very much for watching. I'll see you next time, and be sure to subscribe to the swankiest math videos on the internet.
I can hear your voice from all the way up here, dear. Won't you please come to me? You'll love it up here, dear. There's a light where I float that erases all black. It makes everything